EMS webinar. We will start today with this webinar that is organized jointly with the Catalan Association of Meteorology and the European Meteorological Society. Thank you all for being here. And today, Bernat, Jiménez, Esteve will give this session. Thank you, Bernat, for accepting our invitation, and we are very happy to have you here as an expert of this topic. I will introduce you briefly, Bernat. Bernat is an atmospheric scientist working at the intersection of atmospheric dynamics, climate variability, numerical modeling, and artificial intelligence applied to weather and climate research. After training in physics and meteorology at the University of Barcelona, he earned his PhD in Switzerland in 2019. He's currently a postdoctoral researcher at the Institute of Geociencias at the University Complutense of Madrid, and also an adjunct professor at the University of Barcelona. And his research has focused on the dynamical drivers of climate variability, extreme events, including remote influence of El Niño on European climate, and the atmospheric mechanism controlling the intensity and persistence of heat waves. He has worked at Geomar at the ETH Zurich, Meteomatics, and Barcelona Supercomputing Center, contributing to the development and evaluation of high-resolution weather and climate models. Now, his current work investigates how newly developed artificial intelligence-based weather prediction models can be used for the attribution of extreme events to anthropogenic climate change. He is particularly interested in understanding how human-induced warming affects the likelihood, intensity, and physical drivers of extreme weather. And the title of his session today is What Caused the Unusual European Winter of 2025, Internal Variability, Teleconnections, and the Role of Climate Change. So the floor is yours, Bernat.
Okay, thank you, Mireia. I'm going to share my screen. Okay, wait a second. Can you see my screen?
Yes.
Okay, I can see that.
So more or less, your talk will be around 40 minutes, and then it will be time for questions. And so please raise your hand when you would like to ask a question, but this will be done at the end of his speech. Thank you.
Okay, so yeah, so today I'm going to be talking about something that happened last winter. I know we are all now suffering suffocating heat waves across Europe, so maybe this is a bit refreshing for some people. So yeah, this is work I did together with people from Instituto de Geociencias, which is where I'm working at the moment in Madrid for more than 2 years. And yeah, so this talk will be about the dynamics and also remote influences that maybe have influenced this last winter. So let's start by characterizing last winter. First of all, usually let's look at temperature, because that's usually a more well-behaved variable, as we will see. So how was last winter? Winter is usually defined as December to February anomalies, average temperatures in this case. So globally, we live in a context of global warming. This is evident especially this summer, but sometimes regionally, we still experience colder than average conditions. So yeah, it's important to note that. So globally, the temperature this winter was 1.46 degrees above pre-industrial levels. So yeah, the planet is warming. Although in some scattered areas we saw colder than average conditions, especially for example over Europe. On average, on winter we saw slightly warmer conditions over the south, Mediterranean, and western parts. While it was overall cold over the north, especially Scandinavia and parts of the Baltic countries. If we look into a bit more detail, we see different we see an interseasonal variations. No, December was mostly warmer than average over the northern parts of Europe, including Scandinavia, Iceland, and Russia, while it was close to normal near Iberia and the Mediterranean, a bit warmer than average. While then the pattern really changed in January and February. January and February, we experienced cold wave over Northern Europe, especially Scandinavia, while it was close to average in the Mediterranean and western parts, while February also experienced above normal temperatures in the Central and Southern Europe, let's say. So in general, this last winter was the second coldest in the last 13 years, and it was the anomaly when average over the entire continent was close to the reference climatology, which in this case is the 1991 to 2020 climatology. So it was not an extreme winter in terms of temperature; it was very close to the current climatology, let's say. What it was really exceptional was the precipitation anomalies, and I'm sure if you live in Western Europe, like especially Iberia, France, or Great Britain, even Italy, you experience a very wet winter, and this is what these anomalies tell us. So these are precipitation anomalies compiled by Copernicus using ECMWF data. So we see that especially January and February experienced very wet conditions over Western Europe, including Britain, parts of Western France, Iberia, and the Mediterranean, and also during February. Now we will look into more detail about these different anomalies, but the general picture is this. It was above average wet in many areas, especially in the West and Mediterranean, while it was unusually dry over Central Europe for December, and later over Scandinavia, it was mostly dry, especially January and February. This kind of pattern suggests a high cyclone activity in the Atlantic and a predominantly westerly flow, as we will see. We can see this by seeing that the highest anomalies of precipitations are concentrated in the western areas of Iberia and the different mountain ranges, for example, here in the Balkans. Okay, actually, in terms of another metric to measure precipitation is the number of wet days. And Copernicus has this new in the website where they found that actually between this period of 1st January to 20th of February, some parts of Western Europe, parts of France and Iberia, and the darkest blue areas that we see in this map experienced the highest number of wet days on record since 1979. So it was really, really wet. So it was not just our feeling, it was really a matter of fact. On the other hand, as I was saying, consistent with the lower precipitation anomalies, we also see a record few number of wet days over Finland, the Baltics, and Scandinavia. So the question we ask ourselves is what circulation anomalies could be behind these extreme precipitation anomalies? But before that, let's look a bit into more detail at this maximum accumulated precipitation. So these maps here show the percentile of maximum precipitation during different accumulated windows. The first one is for 1 day maximum precipitation. So these very blue colors means that at least some day during winter, we experience somehow an extreme precipitation in some of these grid points. If we do 7 days accumulation window, so we do the same for 7 days accumulation window, for 15, for 31, 61, and 91. And it's what's really relevant, for example, is that we see very high percentages of accumulated precipitation for this 31 precipitation window over the western parts of Europe, especially Great Britain, France, parts of Iberia, and the Mediterranean. So it's important to say that we'll look a bit into more detail now, but I'm not going to focus on specific station-based measurements because this is not my field of expertise. So I'm going to analyze more the large-scale flow. And for that, we are going to look into different regions. We look together with my colleagues at IGEO, we look at different areas that were affected by these high precipitation amounts, and we focus on Iberia, France, and the UK. And especially for these different areas, we look at the periods where we saw the maximum accumulation of rain for one day accumulation window for 7, for 15, and for 31. I'm not going to go here into much detail, but we see, for example, that for Iberia, this very wet period happened between mid-January to mid-February. While for France, it happened a bit later. It was mostly February. So it started 30th of January until 1st of March. And this was caused by this series of storms which were named. Usually meteorological agencies name storms that are expected to have a high impact on the society, on the population. Therefore, those named storms were quite intense in some way. So we saw this high number of named storms affecting this sector, the southwest sector of Europe. Here, just a few of them from January and February, basically, which is the wettest periods we observed. So from now on, we are mostly going to focus on this period of heavy rainfall. In this plot here, we plot the time evolution in the x-axis from 1st of December to 1st of May. And in the y-axis, we plot the accumulation time window. So and the colors show the percentile anomaly. So what does this telling us? So this is telling us that we saw very extreme precipitation, so above the 99th percentile, for periods accumulation windows ranging from weeks, from 1 week basically to a bit more than 30 days. And we're mostly going to focus on the window of 30 days because at the end we need to pick up something. But yeah, this gives us an idea that it was really extreme winter during this period of time, which also coincides with the naming of the storms that are here also shown in these vertical lines. These are the storms that were named storms that were affecting Western Europe. Different colors denote different meteorological agencies naming them. We also, if we look at the same for France, we see something quite similar. Here, the gray points represent record-breaking measurements, or yeah, this is satellite-based measurements, but record-based precipitation amounts. And for France, we see it was from accumulation windows ranging from 15 to 90 days. This is the whole season. We see really record-breaking accumulation of rainfall over this area. While for Iberia, when we average over the entire peninsula, it was not record-breaking except for this grid point, for this specific combination of accumulation window, but it was not overall a record-breaking event when averaged over the entire peninsula, but even though it produced local records for sure, but not at the global, not at the regional level. Yeah, so yeah, here we see these two different regions, and while for France it was record-breaking at monthly and sub-monthly timescales, for Iberia it wasn't, but it still was very extreme. To understand this a bit better, let's look at this animation where we show the total column water. That's the amount of water vapor that we have in the atmospheric column, together with the water vapor transport, or water vapor flux here at 850 hectopascals. This is an animation that starts on 15th of January and goes up to 15th of February. We see this succession of what we call atmospheric rivers, which are these narrow corridors of high humidity that is transported from the equator towards mid-latitudes. So we see also a lot of cyclone activity. These low pressure centers. I mean, if you know meteorology, you're very familiar with them. So this quick succession of storms or cyclones that were propagating over these parts were transporting a lot of humid, moist air from lower latitudes towards Western Europe. Okay, another variable that we can look at the zonal wind. That is an indication of where the jet stream is located. The jet stream is this fast river of air, very sharp, that it's the boundary between the cold air in the poles and the warm air in the tropics. So this also is related to the storm track activity. And we saw that during this winter, it was quite strong here, as we see by the blue purple contours, and it was quite south. Later, I'm going to look into more detail at different metrics, but here we already have an impression. It was quite south, and it was it's also very, very intense in some places. For example, here during the 5th of February. Okay. So to analyze if the jet stream was in a non-climatological state, we use this eddy-driven jet frequency variable, which is described in this paper by Barrio Pedro et al. And we see here, we plot the anomalies in the jet frequency, So we see increased frequencies of the jet over the southern parts of Europe, and a decreased frequency of the jet over the northern parts. So this is and this is average for this period of time between mid-January to mid-February. So this suggests what we already were expecting, a more south displaced jet. In this paper, we also developed different metrics related to the jet. Some of these metrics are related to the intensity, the sharpness of the jet. I'm not going to go into detail, but more information in this paper if you're interested. What we saw is, like, for these different parameters, what made the jet really extreme was the intensity. So we experienced record-breaking intensity for this 30-day period of the jet stream, and also record-breaking sharpness. Sharpness, as I say, it's very correlated to intensity. While for latitude, it was more located further south than the climatological conditions, here represented by this box plot, but it was not record-breaking. It was within what it's already been observed before. And in terms of extension, very close to climatology, and in terms of tilt, a bit less tilted, so more zonally oriented jet, but also not surprisingly extreme. So what was really extreme was the intensity. Okay, this is a bit technical, so I'm going to go a bit fast. If you're interested, just please ask me later. But this type of diagnostics, what we call the barotropic generation rate, allows us to kind of quantify the effect of the cyclones or the fast traveling eddies on the jet speed. So with this diagnostic, we also observed that the jet was accelerated, here denoted by this blue shading, which is a negative barotropic generation rate. So these blue areas denote that the cyclones, the fast traveling eddies, were depositing eddy kinetic energy into the jet. So they were giving energy to the jet over this area. And the orange area denotes the areas where the eddies are extracting the energy. So the eddies were contributing to make this jet more zonal, let's say, less tilted and more strong and intense towards Europe. Another metric that we look also in terms of dynamics is the Rossby wave breaking. Those are related to these amplified waves in the atmosphere. They can break anticyclonic or cyclonic. And this is not time for explaining them in detail, because otherwise it gives a full lecture. But what we saw is that there was increased frequency of cyclonic Rossby wave breaking north of this accelerated jet, here by the black contour, and there was an increased anticyclonic Rossby wave breaking in the south of this accelerated jet. And why do I say that? Because previous papers have suggested that these cyclonic Rossby wave breaking anomalies and anticyclonic Rossby wave breaking anomalies are a clear signature of what we call a family of cyclones. So when cyclones develop after each other very in succession, or what is also called as cyclone clustering, serial clustering, which is described in this paper of Dacre and Pinto of last year, which is a review paper, very interesting if you're interested in the topic. We can see, it's a signature of these successive cyclones developing one after the other. So since cyclones seem to be very important for these jet anomalies, we also did some tracking analysis. So using this algorithm by tempest extremes, we computed the trajectories of all the cyclones. So the cyclones using this code package can be located using the sea level pressure minimum, and then we apply some thresholds, like the sea level pressure has to be above a certain threshold, 1,015 hectopascals, and there needs to be a certain Laplacian in the same point. Laplacian is a measurement of the rotation or vorticity around this point. So this minimum of pressure needs to be related to some rotation, and then you also impose a series of other restrictions, which I don't have time here to go into detail. But if you are interested, just please ask me afterwards. So this is the climatology we obtained for this era 5 period. We're using just sea level pressure to detect these cyclone centers. And we see that climatologically, as we expect, cyclones are more frequent over these areas, over close to Greenland and Iceland, and they follow these trajectories from the American continent to Europe. So yeah, cyclones are more frequent in Northern Europe than in Southern Europe, and also we see a maximum location over the Italian peninsula. That's what is so-called the Mediterranean storm track. So storms also tend to form in the Mediterranean quite easily. Okay, what happened? This is for the climatology. So what happened during 2026 or 2025-2026, so the last winter? We see, yeah, significantly more cyclones over this western part of, well, Eastern Atlantic, western part of Europe. And let's look at the anomalies, which will be more easier. So this part here just shows the anomalies. So the difference between last year minus the climatology. So the difference between the two previous plots. And we saw what I just was saying. So we see significantly more cyclones over the East Atlantic. So over this box here. And yeah, let's say that these results are not too sensitive of the exact parameters that we use for tracking the cyclones. So yeah, this is consistent to what we're saying. We see more cyclones than average. This is for the entire winter. I'm going to look into more detail into the specific period, but overall the winter had significantly more cyclones, maybe about 8-9 cyclones more than what we typically have during winter. In terms of percentiles, it was extreme. So let's say most of the grid points here in terms of cyclone frequency were above the 90th percentile of all winters. So yeah, it was an extreme season, but only a few grid points show record-breaking number of cyclones for the entire season. The message changes a bit when we look at the maximum, the 31 days window with the maximum number of cyclones, which you plot here, the plot in the right, where we saw actually that for the maximum 30-day one window, we recorded the record number of cyclones over this this region between Britain, France, and Spain. And if we also, this is in terms of percentile, so clearly above the 99th percentile, this is record-breaking. Almost one cyclone every day. There was almost one cyclone every day for this period of time. And regarding the timing, here in this plot, we can see that this peak of number of cyclones happened around the 29th of January and the 8th of February. That was the location, the time where it occurred. So it's consistent with the precipitation extremes that we saw. So the maximum number of cyclones occurred when we had the maximum or the extreme precipitation events. Okay. Maybe some people are also more familiar with the NAO. And the NAO is a teleconnection pattern that describes this variability in the Atlantic between the pressure difference between the Iceland and the Azores High. So this pressure difference, this dipole can vary at different timescales, from daily to decadal timescales, as we see here in this plot. Here, this plot shows the NAO index for monthly values over this period from 1950 to 2026. I don't have time here to go into detail because it will take too much time, but we know that during a positive NAO, we expect storms to propagate more north, and be more strong, probably going to the UK or to Scandinavia, while usually then in the Mediterranean, it's very dry and very settled weather. While if we have a negative NAO state, storms tend to propagate more zonal and directly impact Spain, France, and parts of the Mediterranean. So if we look also, this is the NAO, and if we add another mode of variability, which is the East Atlantic pattern, we can describe the flow using these two modes of variability. And as I say, this is just to make some consistent analysis. But the interesting point here is that these two main teleconnection patterns that describe the state of the circulation. They explain more than 60% of the variability at monthly timescales and interseasonal timescales. So this 2 modes of variability, if we have the time series, it gives us an idea of how extreme the circulation was. And we can see here the time evolution of these 2 patterns from November to end of March. And we saw that for this specific period where we saw the maximum record-breaking precipitation over France or very extreme precipitation over Iberia, we experienced negative NAO, which is related to south shift of the storm track and a south shift of the jet, consistent with what we just also saw, and also negative East Atlantic pattern, which is this monopole anomaly here that denotes more, if it's negative in this case, will be indicative of more cyclonic activity over this area. So a bit related to the cyclones we were seeing in this area. So the East Atlantic pattern was really negative, was almost 5 standard deviations below, negative. So during this period of time, the 2 patterns coincide having negative values, and that was related to the intensity of the jet and also the south displacement, which led to the very extreme anomalies, precipitation anomalies. Another perspective is the weather regimes, which also here I'm not going to explain, but just to say that this weather regime perspective tries to decompose the atmospheric flow, the atmospheric circulation into different patterns. In this case, usually for the Atlantic, it's usually 4 patterns. These are provided by ECMWF for the forecast. So how these different weather regimes look like during winter. So the plot below shows you the dominant weather regime for the different days, starting in January until end of February. And we saw also that using this different approach, which is alternative to the circulation patterns, to the EOF patterns that I should show you before, it's also consistent showing a negative NAO pattern almost during this period. From the 15th of January to the 15th of February, we experienced consistent and consecutive days of negative NAO pattern. Okay. Until here, we describe a bit more how the circulation was. That explains the extreme precipitation that we observed. But let's now explore a bit if there are any remote influences that could have impacted this circulation anomaly. So let's explore different remote drivers. One remote driver that's usually taken as very important is the El Niño Southern Oscillation, or ENSO, and can have an impact in the Atlantic, but it's not very, very robust in terms of intensity. In particular, this winter, we had cold temperature anomalies over the Pacific. That's what we call the La Niña phase. And so during this winter, we had La Niña phase. And according to literature, that would be more inducive of a positive NAO. So this is very unlikely to have had any effect on the circulation. So let's discard ENSO as a remote driver. Other drivers that we can consider are, for example, the Madden-Julian oscillation, which is very important. It's a very important mode for subseasonal predictability or subseasonal variability, and also the stratospheric influence, which I'm going to describe just very briefly. Also, let's note that, for example, these are the sea surface temperature anomaly map during December and during February. We see that overall, over the planet, temperatures were much warmer than average, and especially over the Atlantic, these very warm temperatures could have also contributed in making these weather systems, the very powerful cyclones, more intense, or even not maybe intense is something more difficult maybe, but at least more moist. We will look at this later. Okay, so the MJO, that was the next possible remote driver. The MJO, very briefly, this is not to talk about the MJO, and I'm also not an expert, but this MJO is this propagating convection pattern that propagates from the Indian Ocean into the Pacific Ocean. And it has a period of 30 to 60 days. It can be more intense. Sometimes it can be weaker, as we see here. So it's this propagation of this convective wave. And the MJO can also, as I will say, can also have an impact on the extratropics, can change the weather patterns also far away into extratropics, into the North Atlantic and Europe. But first, how was the MJO during the last winter? The MJO usually measured in terms of these 2 indices, which basically tell us the farther away from the center, the stronger the convection was, And depending on the quadrant, we see the point, the convection is located in a different position. For example, if it's in this quadrant, the location is located over the Indian Ocean, or if it's in the phases 4 and 5, the location is located over the maritime continent. If then it's in the 6 and 7 over the Western Pacific, etc. So during last winter, here we plot from 1st of January to 31st of March, January in red. So we see that January, especially during the starting on the 10th of January, going until the 22nd, we experience very consistent and persistent phase 6 MGO, and also later phase 7 MGO. And what literature tells us, especially according to this paper from Lee et al. From 2022, is that, well, in this paper, they study how the MGO can influence the frequency of different weather patterns over the Atlantic. And specifically, the phases 6 and 7 can enhance the probability of having NAO negative states, as we see here. Here, positive values denote enhanced probability of NAO negative states. And yeah, also combinations of NAO states with other weather regime states, especially these TV state, which we see here. It was very enhanced during phase 7. So that could have played a role. I mean, a more detailed study needs to be done to really say that, but at least previous literature suggests that. It's also important that the MGO can interact with El Niño. There's a lot of literature on that. Just to say something, for example, this paper, which is a very good paper reviews the interaction with the El Niño, ENSO and the MGO, they find that if La Niña occurs together with the MGO phase 7, we also expect increased probability of a negative NAO in the Atlantic, what we just had, and also propagation through the stratosphere. And that brings me through the stratosphere, which I also, sorry that I don't have much time to explain the details, but we know the stratosphere is this layer of the atmosphere between 10 kilometers and 50 kilometers. It's very dry, there's no convection. But in winter, there's a polar vortex due to the polar night. There's a polar vortex that develops, and this polar vortex in the stratosphere can break apart. So when this polar vortex breaks apart, we had a weak vortex event, or when this polar vortex gets stronger, we have a strong vortex event. And what this flow shows, discovered by Balgin and Darkenton in 2002, which is called the dripping pane, by how it looks like. So it shows how the stratospheric anomalies, here represented in terms of the NAM index, maybe some people know, can propagate downwards and have an influence in the troposphere. And during a weak vortex event, we tend to experience a more negative NAO state, while during strong vortex events, we tend to experience a more positive NAO state, so a more forward displaced jet in the Atlantic, in this case. What happened last winter in the stratosphere? Just very briefly, we had a sun stratospheric warming. That's also a very extreme event that happens in the stratosphere, and it's related to a totally collapsing vortex in the stratosphere, so very strong weakening of the polar vortex, which is denoted here by these blue colors. Blue colors is a negative NAM, weak polar vortex. And this will be similar to the dripping pane plot that we just saw. And although it's not that clear, that it seems that this event could have played an influence on the downward impact. So here we plot the different pressure levels. So at the surface, we see a negative NAM index, and negative NAM index is very closely correlated with the NAO. So, and this period here is the period we saw the maximum precipitation, no? So these could have had an impact from the stratosphere. But of course, more detailed studies are needed to really say that. Just to say some words on it. It could have played an influence, but more work needs to be done. Especially more probably model experiments need to be done to really disentangle these different contributions, because at the end, the atmosphere is very chaotic, and the different teleconnections interacting between them, they can lead to nonlinear effects. But yeah, I would say that there could have been an influence from the stratosphere. Okay, so we analyze now the teleconnection. Let's jump into the last part of my talk, which is a bit to assess the role of climate change. So observations tell us that in the Mediterranean precipitation, there is no robust trend. So observations so far don't show any trend in winter precipitation. at least at the Mediterranean scale. Maybe locally, some stations show some trend, but on a Mediterranean timescale, the variability, internal variability still dominates, decadal variability and intraseasonal variability. What CMIP6 projections say, CMIP6 is these experiments that make future projections based on climate models. Climate models are suggesting that there will be a drying of the Mediterranean region and a more increasing precipitation or wettening of the Central and Northern Europe in winter. Although, as we see here by the hatching, these trends are still not, or these signals are still not robust. We expect the internal variability to dominate and the intermodal difference is still very large. So these trends are not robust yet, but that's an indication. And yeah, as I said, there's a strong internal variability and we cannot be sure. But this is on the average, no? So extreme precipitation, extreme rainfall is projected to intensify in many regions. And sometimes you can have increasing extreme precipitation, especially in daily maximum precipitation, but having a decrease in the total precipitation. And that's usually what we will observe in the Mediterranean and Southern Europe in the next years. Probably a decrease in the precipitation, but not necessarily the extreme values. Extreme values are likely to increase, especially at least in climate models. If we look at high resolution models, this increase might be even larger, no? Because we can better resolve the convection and so on. It's important to know, yeah, we have two contributions. The thermodynamic contribution, which is the typical statement that people say, okay, a warmer air can hold more water vapor, and therefore if it precipitates, then it precipitates more water. That will be the thermodynamic contribution that will explain that, yes, when it rains, it will rain heavier. But then there's the dynamical contribution, which is more uncertain, and really, which is this one here shown in C. In many places, not significant. We don't actually know what's going to happen, no, in detail in many areas, especially if we go at seasonal level and so on. Precipitation trends are very, very, especially in the extratropics, very, very model dependent and still very uncertain. Okay, last thing of the talk. So one other possible approach to assess the role of climate change is to do what is called an event attribution. These event attributions are exercises that scientists do to try to assess how climate change have modified certain characteristics or certain return periods of an event. And in particular here, I'm going to use this forecast-based attribution approach using AI weather models, which we just published a paper last month, applying this to extratropical cyclones. As I say, I don't have time here to explain this paper, but feel welcome to read the paper or directly contact me. This method allows us to quantify. It's a storyline-based approach. So we simulate the event in the present world, and we calculate how much did it rain and how the event developed. And we also calculate the simulation in a pre-industrial climate. So we remove the global signature of climate change in temperature and humidity, and we resimulate this event from the initial conditions and try to see if the evolution is different in a pre-industrial climate or not. And well, in this paper, we applied this to these two cyclones, and we use the AIFS AI model, which is developed by ECM.WF, and it's a graph neural network. Yeah, here's some details. I don't have time, but well, you can read or ask me later. First step you need to do when you do an attribution event is that you try to simulate the event and see how well does the model. So for this event that happened between 4 and 6 of February, we saw the first panel is era 5, the total accumulated precipitation during this 2-day period. We see that this is the period that caused severe damage and severe flooding over Grazalema and parts of the Strait of Gibraltar. Of course, era 5 cannot capture these local extremes, but here we are interested more in the large-scale picture. But okay, the message here is the model could reproduce the forecast up to 5 days. So it was a good forecast. And then by simulating the event also in a colder climate, the pre-industrial climate, we can assess how the precipitation would have changed due to climate change. And this is the result. So the result is that we see increased precipitation over the central part of the peninsula, but actually we see decreased precipitation over the Strait of Gibraltar, the southern parts of Andalusia. So yeah, the responses sometimes for these events, these attribution exercises are made for specific events. So sometimes the reply you get, it's very complex. It's not always as, oh yeah, all cyclones get wetter, all cyclones, it rains more. No, sometimes the climate change have maybe favored the precipitation, other times might have even reduced the precipitation. So yeah, it depends on the event. And this is a clear example that for this event, it redistributed the precipitation, but if we average over the whole peninsula, as we see in these two walk plots, there's no significant changes in the precipitation. And yeah, that's the final exercise we also tried. So this is for one event that happened, Storm Leonardo, that happened between the 4th and 6th of February. So if we now run the model for this entire 31-day period episode between the 15th of January to the 16th of February, that's to say we ran 156 AIFS simulations initialized every 6 hours, and also 146 more runs in the pre-industrial climate, we can see the contribution of all these different weather systems on the precipitation. No, basically, in short, saying it shortly, this is the changes in the accumulated precipitation in the present world compared to a world where we have removed the global warming, let's say. And we see, yeah, present world, like global warming, would have likely enhanced precipitation over France, Britain, and parts of Central Europe, but actually over Spain, the pattern is more complex. We see this decreased precipitation due to climate change over the south. Some parts precipitation might increase, other parts it might decrease, so it's a complex pattern. We can also look at different variables, but for example, the wind doesn't look significant. So climate change didn't seem to change dramatically the winds, but it has changed the available moisture in the available total column water. So the total column water was increased, especially over these areas. It was not significantly enhanced over the peninsula. Maybe that's the reason we don't see a very clear pattern there. But one could think, oh, okay, this is just a model, just one artificial intelligence model. How can we trust it? Actually, I went into this other tool, which is a global. It's a similar, let's say, methodology, but they use a climate model and they nudge the circulation towards Era 5. So they simulate the events in the present climate and in the pre-industrial climate, and they nudge the circulation. Let's say they keep the pressure fields and the geopotential fields close to the observations, and they see how the other variables change. And in this case, this is the accumulated precipitation change between the present day and the pre-industrial climate for the same period of time. And we see that the patterns using this climate model, which is state-of-the-art climate model, is very similar to what we obtained before with the AI model. We see decreased precipitation over southern parts of Iberia, some patchy patterns over the Mediterranean, so not very clear signal, but mainly this increased precipitation signal over, France and the UK. So there's a qualitative agreement across these two independent frameworks, which also increases the confidence that there's some regional signal in the impact of climate change, at least for this episode. This is an approach that allows you to quantify the climate change impact on a specific event. Okay, so now wrapping up, just sum up what I just said, like last winter was extremely wet, especially over Western and Southern Europe. It was associated with a record-breaking jet stream intensity and a relatively southern position of the jet. We observed record 31-day maximum cyclone frequency over this eastern North Atlantic region, which is consistent with a repeated storm passage into Western Europe. In terms of, so these circulation anomalies were consistent with the NAO East Atlantic pattern variability, and we observed possible remote contributions from the MGO in the tropics and from the stratosphere. And finally, in terms of climate change, we say there is no robust climate change trends on average if we analyze the precipitation over winter as a whole. but forecast-based and nudge storyline attribution suggests that global warming could have enhanced rainfall over France and the British Isles, while maybe decreasing it in some other parts, especially close to the southern part of Spain. Yeah. So that's all. Thank you for your attention, and I'm happy to take any questions.
Yes, applause. No? If we would be in person, we would clap our hands. Thank you very much, Bernat. I think you have done a very clear, well-documented session and talk. So now it's time for questions. I suggest people raise their hands, and probably the best option is to unmute when I give you the turn. So yes, so if I am correct, David Pino raised the hand. So please go ahead with your question.
Thank you very much, Bernat, for this nice presentation. I have a comment about the different time scales you present at the beginning of your presentation. That this is, I think this is something that is really interesting, and this is something that we are observing not only in this Atlantic precipitation, but also in the Mediterranean. So my question is directly, so my feeling, and this is only a feeling, that this episode that we had this winter is not only related, so the total amount of precipitation is not only related that we get different cyclones, but also that the intensity of the precipitation in the short scales was, to my opinion, a bit larger than usual for winter. And this is related with what you mentioned about the Mediterranean, that maybe the amount of precipitation will decrease, but not that much, but the intensity or torrentiality will increase. And this is especially strange for winter. This is something that they have some data in Central Europe as well. So the intensity of precipitation increases. So what is your comment about this?
Yeah, so yeah, I think that's like, maybe that's why we see some, okay, like the, yeah, my intuition and what I've seen also is that also in many studies is exactly what you say, you know, like daily and even sub-hourly or like sub-daily extremes are increasing. Like storms can become more powerful because of more latent heat release. This is something that maybe it's more common in mesoscale and microscale processes. So I don't know the impact. I mean, this is a very interesting line of research, no? Because we see like if we increase the resolution of the models, these climate models, people start seeing like this, maybe there's maybe an underestimation of these extreme daily events. So maybe that's something we are not really seeing well in these CMIP6 simulations, that maybe we're underestimating a bit. Did I answer everything? Maybe.
Yeah. Exactly. What it's much more difficult for climate models to project this type of extremes in the near future or in the future. Because you need to have a really high resolution in order to analyze this daily. This is what you mentioned. So totally agree with you. Thank you very much.
Yeah, for example, in this direction, I mean, there is this study that done by Carlos Calvo et al. Maybe you read, where they do this for this kind of the same approach I did here, but using a WRF, using a very high resolution local model, and then you can really see that at local scales, these mesoscale systems can really become much more extreme than what the CMIP6 models, the global climate models, maybe suggest. Yeah.
Thank you.
Okay, more questions from the audience. Raise your hand if you want to speak. If not, we have also a chat question.
Let's see.
Yeah, maybe you can read, Bernat, but I can read it for everyone. So Abdelaziz, PhD student, asks about if this phenomena can happen sometime in the near future. should this be expected, or is it the last time it happens for a while? Is an indicator that the coming years will be dry years and more warming? What would be weather would be like these areas? Yeah, it's a lot of questions.
I mean, I would say, like, if it will happen in the near future, I mean, if you mean this very wet spell of monthly and sub-monthly wet period, I mean, we don't know, because this is probably driven by internal variability. And as I was saying, this internal variability is something that is superimposed from climate change, and still, like, dynamical changes in the storm tracks are very, very uncertain. So in the following years, let's say 10 years, it will still be similar. What is going to change is maybe not similar. I mean, the variability will be more, still not dominated by climate change. It will be dominated by internal variability, although climate change can make specific events more intense. Not all of them, but some events can become more intense, especially precipitation at local scales. Yeah, can become more intense. And what else? Dry areas. I mean, actually, one of the reasons the Mediterranean is dry, there's a trend. The Mediterranean has a trend to get drier, and this is because also, like, models project an expansion of the Hadley cell, and of course more subsidence over the Mediterranean that would make the atmospheric layer more stable and less easy to have vertical ascent. That's also an important player, because for example, most of the changes we see here, so climate change can have a direct impact by Clausius Clapeyron. Yeah, there's more water availability in the atmosphere, but also can decrease the stability. If we warm more the upper layers, the vertical movements will be less strong. So yeah, there's two factors that play a role.
Yes. Okay. More questions? No, there are no hands raised, if I am correct. If not, correct me. Yeah? I can ask a question. Okay. What about this? Why do you use these AIFS models? I have seen, during your presentation that at the beginning now, and also, is it? I guess the results are comparable with the ERA5 in terms that the AIFS has learned from ERA5, or what is your opinion about this output from this model?
Yeah, my opinion is that for weather forecasting, which is what I'm using them here, they are almost, they are the same or even better than the physical-based models. Of course, their success is because of, in first place, we had a very good physical model or numerical model that we could train this model with. So yeah, I mean, it's surprisingly good. It still has maybe some biases in smoothing precipitation patterns. For example, here in this plot, this is ERA5. And if we compare to the forecast of the model in the different lead times, we see that the precipitation patterns are a bit more blurry, a bit more less local, more spread, let's say. Yeah, so that's a problem of the well-known bias of these models, or a well-known limitation. But I guess they will keep improving. So also the resolution of this one is 0.25, but they are already building models at higher resolution. And the main advantage is that they are much efficient to run.
Yeah. Okay. Yeah, less computing demanding. So for large scale patterns, I guess you can use them in the same way as the physical ones. Okay.
Yeah, that's what we tried to show. Well, in this paper and a previous paper, before doing this attribution analysis, of course, we verify that the model, the different AI models, we actually tried 4 different AI models. We verified that they are accurate at simulating the different events. So, yeah, you always need to make sure the forecast is good before taking any conclusions.
Okay, thank you.
Yeah, you're welcome.
So, okay, let's see the chat. Yes, there's another question. from Branco Grisogono. Nice to see you here. When the mean temperature gradient between the tropics and the polar regions get smaller, when this happens, why the jet stream gets stronger in your plots? It is about waves or what?
Okay, yeah, I mean, it's a very, very interesting question. Thanks for asking. I didn't analyze if this specific winter had increased temperature gradient or not. I mean, this is a common consequence of climate change. Now, the Arctic is warming faster than the tropics, so we expect that the difference between the Arctic and the equator will get weaker, and therefore there's many people or many research papers showing that we expect a more meandering jet because we get less difference, and then the jet needs to get weaker. But actually, we are in the upper troposphere, we get the opposite effect. Like the upper tropical troposphere is warming faster than the polar upper troposphere. Therefore, we have a tug of war, what it's called, like at upper levels, actually, they are trying, the temperature anomalies are making the jet stronger. And at lower levels, they are making the jet weaker. And therefore, there is this competition between the different mechanisms, and that's also one of the reasons why there's no very strong signal in climate models. It's not that simple. I know media have used that mechanism a lot to explain, for example, the extreme events, the heat wave. Like we say, the poles get weaker, and therefore we get more meandering jet. But I would say, from a scientific perspective, this line of story is not always that clear, especially for specific periods of time. So, I mean, for this specific winter, maybe that was not relevant, this temperature difference.
Okay.
Thank you very much.
You're welcome.
I appreciate your answer.
Yeah. Thank you for asking.
Okay, more questions? No? If there are no more questions, I think we can finish here the session. Thanks again, Bernat, for your talk. Very nice talk. Thank you, everyone, for being here. Yeah, we applause and see you next webinar. Please, thank you all for coming. Good evening. Thank you. Thank you, Bernat.
Good evening.
Bye-bye.